by Professor Pravin Varaiya of Berkeley about predicting intersection signal.
So this is a strange talk because it doesn't have too much mathematics, there's no game theory, and there's no congestion. So you wonder what is there. So it's a talk about intersections. And so this is my summary. The first propositions is that intersections are the bottlenecks of urban roads. And therefore, intersection signal control, which is how you regulate traffic through the intersection, determines mobility, which is throughput, how many people can go through, and delay, how much time they spend in the intersection. And there are three sets of control parameters which determine the control policy of an intersection. The first one is cycle length. So I'm going to define all these in case you never heard of them. The second one is phase duration, so how much green for one direction versus another. And the third one, which is probably less familiar, is offsets. That is the displacement of the beginning of green from one intersection with the next. And then I'll move to adaptive control, where the duration varies depending upon the sensed traffic by the controller. And then predicting how long a particular phase will last, and some applications why people care about that. And so I said intersections are bottlenecks, so let's look at that intersection, sort of a typical four-leg intersection. And in those four legs, there are two lanes. There are three lanes, but let's just look at the left turn lane and a through lane. The right turn lane, I assume, is always permitted, so there's nothing to do with the intersection control, right? Because the right turns are always permitted. And so let's assume, so there's four approaches, one through and one left turn lane. A typical number about how much capacity, how much flow can one lane carry is a number to remember is about 1,200 vehicles per hour, right? So 1,200 vehicles per hour can go through one particular lane. It may go as far up as 1,800, but that's just for purposes of this. So the access capacity, the number of vehicles which can enter that intersection is, you have 8 possible lanes, 2 in each approach. So 8 times 1,200 is 9,600 vehicles per hour. That's the access capacity of that intersection. However, the intersection can only allow 2 of these movements at any given time, which are non-conflicting, otherwise you'll have a mess, right? So only 2 are permitted, so that means the intersection will permit at most 2 times 1,200 or 2,400 vehicles per hour, which is 25% of the access capacity. So the intersection is the bottleneck, right? It can only carry 1/4 of the throughput that the roads can bring to it. So the performance of the road network is determined principally by how the access to the intersection is controlled, right? That's usually by means of signals. Either you have green, in which case you can go, or it's red, in which case you shouldn't go. And so the signal control parameters are something cycle length, and the phase plan, the phase durations, and the offsets. So this particular intersection, we have each movement is called a phase, so there's 8 phases. The odd numbered ones correspond to turns, and the even numbered ones corresponding to 3 movements, right? So that's just something to remember. If you talk to a traffic engineer and he says phase 1 and phase 5 are actuated at the same time, that means 2 left turns are actuated at the same time. So typically in a phase plan, you'll have 2 phases that are actuated, get a green at the same time. Then you switch to another 2. And then you switch to another 2 and another 2. Right? So that's how these 8 phases will get actuated. And then you come back to the beginning of the cycle. Right? So a cycle will consist of sequence of pairs of phases that get actuated. The amount of time that this pair, for instance, is actuated is called the duration of that phase. Right? So that's the phase duration. And the total cycle time coming back is called the cycle time. And typically, I'm going to assume, and that's the case in most places, the cycle time as you come back is fixed. Right? There's a reason for fixing that, but we'll get to that. So for instance, this may have a total cycle time of 120 seconds, or 2 minutes, and you may spend 30 seconds in each phase. Normally that's not the case. In the more heavily traveled direction, you have a longer duration than the other. So now, so you can think about, if you're a queuing theorist, that this intersection consists of 2 servers, right, for the 2 directions, and there are 8 queues, and it can serve 2 queues at a time, but not any 2 queues, because they have to be non-conflicting. I cannot serve this queue and this queue at the same time. So the pairs of queues that I'm allowed to serve, that looks like a standard queuing problem. There's one hitch, and that is every time you switch, right, I switch from this to the turns, there's something called an all-red clearance. So I have 2 greens. Before I switch to another 2 greens, I have to have everybody red. Right? It's usually 3 seconds, called an all-red clearance, so that the vehicles who are not very alert, who are in the intersection, when the phase is switched, they get time to get out of there, right? So that's wastage, right? And so 3 seconds is wasted every time you clear. Yeah.
Disregard right turns in general?
Pardon me? I'm disregarding right turns. In case the right turns have a signal, then they usually, I mean almost invariably, the right turn is permitted at the same time as the through movement. Right? But for my discussion, I'm just assuming that the right turn is permitted at any time, so they don't offer you any problems in terms of usage of the intersection. So if you have a switching, or I mean, serving discipline, the switching creates a big problem. I mean, most of your theorems of server, right, multi-processor, whatever, break down. So there's an obvious thing to do. So supposing this cycle was 100 seconds, and there's going to be 4 switches per cycle, so I'm going to waste 12 seconds in all red. So that's a wastage of 12%. So the obvious thing to do is to extend the cycle. If I make the cycle 200 seconds, again, you just waste 4 times the red. So I only again waste 12 seconds. So that's a wastage of 6 seconds. So the thing to do is to increase your cycle, then the waste goes down. But people don't like increased cycles. They're going to wait for 2 minutes or 3 minutes or 4 minutes. So that's one problem, that people get upset for a long cycle. But more importantly, if there's a long cycle, then there's also a long red. And if there's a long red, the queues build up. And the queues may build up and saturate and affect the previous signal, right? So you have to compromise. You want a long cycle to reduce the wastage, but you want a short cycle to prevent queues from building up. So that's an issue about how big a cycle length you should create. Typically, if there's a lot of traffic, and you'll find that in most cities, the cycle lengths increase. Because now you have a lot of traffic, so if you give them too much red, you'll saturate the signal. And if there's very little traffic at the middle of the night, the cycles are normally shorter, so people don't wait. And there's no reason to make them wait, because there's plenty of capacity. Yeah?
So this analysis is currently non-adaptive.
Not yet. No. So I'll come to the adaptive part. But the adaptive part is principally for phase durations are adapted, not the cycle time. The cycle time are kept fixed, and for a reason we'll come to, which is offsets. So offsets require a fixed cycle time. Okay. So the phase plan determines which sequence in which they're operated. Now the duration. How do I fix the duration? So that's the following. So let's take a phase I. We have somehow or the other managed to fix the cycle time, t, 100 seconds, 200 seconds, whatever it is. Then, so the phase I, g sub I is the fraction of time in the cycle that direction gets a green. Okay? So g sub I is the green time. So g sub I divided by t is the fraction of cycle devoted to phase I, green. sub I is some magical number called the service rate if we're queuing theorists, but normally it's called the saturation flow rate by the traffic engineers, but it's exactly the service rate, which says that if nothing else is going on and you had an infinite queue and this guy was green all the time, SI vehicles per hour would go in that direction. Okay, so that's S sub I. So you have to select these G sub I's, that's the phase duration. S sub I is a physical thing depending upon the width of the road, etc., whether it's a grade or not grade. So S sub I is given physically. T you have already decided, so you have to pick G sub I. There's a constraint which is the sum of the GI, the sum of the total green time you have is the total cycle time minus the loss due to the red clearance. So it's a straightforward problem, right? So this is called a fixed time control. I'm going to fix G sub I for every cycle. There's nothing adaptive here, right? There's a fixed time control. And so the G sub I's are constant that you will select. And they must be chosen to accommodate the demand. So depending upon how much demand there's approach in the through directions from south to north versus east to west, you have to select the G sub I so that C sub I will be larger than your demand. Okay? If I give you the demands, it's a straightforward problem to figure out C sub I. There's some flexibility as to how you should choose GI, and because you hopefully the total rate available is larger than your demand, then you can distribute the excess either for in all directions or a particular direction where there's greater uncertainty about the demand and so on. Offsets. So here's 6 intersections, and they're connected the way I have written them. Now, let's look at this direction from west to east on the bottom. So this phase, this will be a through phase, so it'll have a number 2, 4, 6, 8. Let's suppose it's phase 2. So phase 2, let's say, starts at time 0 in a cycle, right? So just do everything modulo the cycle. So it starts at 0. Vehicles, they just got released. Then this phase will start at some time, maybe 0, maybe some other time. Well, you don't want it to start at 0. What you want to do, if it takes a certain travel time to hit here, then you want this offset to be exactly equal to that travel time. Right? Then you get a green wave. Right? I started green. It takes me 5 seconds to get here or 10 seconds to get here. Then I want this green to start 10 seconds after this one. Is that clear? And then this takes 7 seconds. So I want this green to start 7 seconds after that one. So that's the displacement of the beginning of green is called the offset. Okay? And the offsets are very critical because that determines whether everybody, I mean, if it's bad offset, then I only hit the red light every time I cross. And if it's good, synchronized, so-called, then I get a green wave.
We assume implementation-wise that there's a common global clock.
Yes. So implementation-wise, there's somewhere, some intersection, it doesn't matter. Somebody, so these offsets are set by a traffic management center, okay? Which says right now is 0, and the cycle time is 120, and you will start at 0. Your synchronizing phase, which I said in this case is phase 2, you will start 10 seconds later, 20 seconds later, and so on. So it looks easy, but there's a problem. Yeah?
So can offsets also be dynamic?
It can be, right? It can be.
Where is this?
Absolutely. So it should be dynamic, right? The offset should be dynamic. But I'll come to making things so dynamic, right? But before I get to that, even in the static case, there's a problem. The problem is that if I go around a loop, I'm coming back at the same point in the cycle. So theta 1, 2 plus theta 2, 3 plus theta 3, 2 plus theta 2, 1 must be a multiple of the cycle. That's an integer constraint on the cycle. Is that clear? Right? Has to be a multiple of the cycle because I'm coming back. And everything is modulo cycle time. So I should come back at the same point in the cycle time.
Why should anybody come back?
No, nothing. This physically, right? This is 10 seconds. This is 20 seconds. Physically, it should, and if I'm starting synchronizing the green, the beginning of green, then no matter which way I come around, I should end up with a multiple of that green. That's a combinatorial constraint on this, right? Makes the problem difficult.
So the assumption is theta 1, 2 and theta 2, 1 should be the same.
No such, I'm not making any such assumption. Because the speed here may be faster than the speed here, right? If this is the commute direction, this will be slow, and there's nobody there, so the speed, travel time from here to here may be higher or lower. So even in this case, it doesn't have to be obvious, right? But indeed, if I'm just worrying about one arterial with one north-south and one southeast, south-north, it's easier problem, even the combinatorial problem easy. But when I have a network, like a grid, this becomes difficult. Okay? Now, ideally, as you said, it should be changed. But just imagine you are the traffic engineer, and you are told, okay, now your offset is increased by 10 seconds. You cannot implement it immediately. Because the motorists aren't used to sudden change. I expect this to be green for so long, and now all of a sudden you're either increasing it or decreasing my green time, and so it takes some time, over typically 5-10 cycles, you bring in the new plan into operation, right? Number one. Number two, you need the data to be able to figure out what the travel time is. And number three, this problem is not easy to solve. So it's not obvious what is the right offsets. Okay, but I'm not going to consider offsets. But just to give you what is the basics. So the basic transportation engineering signal control problem is just what I said. Offsets, cycle time, phase duration. Now, I'm going to do everything with this particular intersections. This intersection has 6 phases, denoted P1, P2, P3, etc. P1 and P5 are odd numbered, so they're the left turn. P2 and P6 are the main through routes, and P4 and P8 are the other ones, the through in the minor direction. P3 and P7 are not there, so P3 and P7 would be a left turn. So assumption is that if I want to make a left turn, I wait for this green and make a left. So it's so-called permissive green, permissive left. Okay? So there are only 6 phases in this. 2 phases are missing or have 0 time. And let's suppose the plan is that P4 and P8, P4 and P8, which is the through direction for the minor state, come first. Then come P1 and P5, the 2 left turns, and then P2 and P6, the 2 major through movements. I've drawn them purposely this way to denote that this duration and these durations can be varied. Okay? So that's called actuated signal or adaptive duration. So they can be varied. We'll worry about how they're varied. But the cycle time is fixed. So whatever variation you get has to be, if you have extra amount of time, you give it to the major direction. If you have less time, you steal it from the major direction, right? So that's a standard actuated control. How do you decide whether to give more to P4, P8, or P1, P5? Well, you have detectors. The detectors in the ground measure how much traffic demand there is. I mean, it's all imperfect, right? So, but anyway, that's what it's supposed to measure, how much traffic demand there is in this direction and that direction. And if the traffic is higher than you expect, then you give it some more green. Right? If I have more left turns than I expect, I give the left turns more green. And if there's less, I turn the green to red and give the extra time to the through movement. That's an actuated signal. Maybe increasingly more and more signals are becoming actuated. right? Because it provides some adaptivity, because if I notice that there is more demand in here, but it's not long-term adaptation. There's no algorithm which is going to estimate the demand that is coming and doing that. Everything is sort of 1 cycle, 2 cycle, 3 cycle horizons, right? That's the current practice. You would say it is possible that if I see a lot more here, then I know that they will show up in the next intersection, so I can use that to give more time to the through movement in that direction. Okay, so that is done. So several commercial packages look at 2, 3 intersections and decide. Okay, but if this is variable, then you cannot predict when my green will happen, right? Now, you may not care, right? But it is useful, and so that's where I want to go in an actuated signal. So I'm going to look at the durations. So I'm just looking at one direction, right? The major direction. So I'll ignore this one, but the same calculation goes in the other one. So what I want to do is to predict. So at any time t in the cycle, I want to predict, this is the phase 4, and P4N is the end of that phase 4. So it's the end of green, or the beginning of the next red, or the end of that. So I want to predict at this time t, how much time is remaining in the phase 4, how much time is remaining in phase 1, which is the remaining phase 1 plus that, plus etc. Right? So these phases are no longer fixed time, so it's not 20 seconds, 40 seconds, 60 seconds, but maybe 20 seconds plus or minus something, and 40 seconds plus or minus something, and that's a random thing which depends upon the traffic, and that I don't know how much traffic there is. Not only depends upon the traffic, but it depends upon how the controller senses that traffic and what kind of algorithm it is using to increase or decrease the green times. So I want to predict this using historical data. That is, I know historically this phase took this much time, and that's the distribution, and now I want to predict how much time will be left. So that's a straightforward problem. So let's see how you solve this. Now, you may or may not be able to see this. So this is data from that particular intersection. So one vertical line is 1 cycle. Okay? So if I look at cycle number 30,000, that's what happened. So this much green was the duration of phase 4. Then comes the red, which is the duration of phase 1. And then the blue is the residual, which is the direction of the through movement. Right? So there are, for each cycle, I have 3 numbers: the duration of the green, the duration of the blue, and the red, and the duration. Okay?
But this is the result of actuation.
This is a result of actuation. So this is historical data I get from the controller, or rather from something which can sense the signal phase. Okay? So that's what I have. Now, I'm outside my measurement. So this is what I've already measured, and now I'm in a new cycle, and you request for me the phase, how long is the green phase going to last, how much is the blue phase going to last, etc. Okay? So that's called predicting the phase. And I want to know predicting the phase duration.
But you don't know the actuation logic.
The actuation logic is very, very difficult. It's all in hardware. Every company has its own actuation logic. It also depends upon what actually they're sensing of the traffic. The only thing you know, if it's anything decent, then the greater the traffic, the more green is given. But if there's traffic in all directions, then it's unclear who gets the green, right? So typically, to give you a 2-minute description of how these things work, so there's a minimum green, right? You have to have a minimum green. You want to make sure that that a vehicle gets through that intersection. So there's a minimum green. That's one parameter. The second parameter is so-called extension. So every time it sees a vehicle going through, it extends that minimum green, let's say 2 seconds. per extension. Up to a maximum. You don't want to steal everything from the other vehicles, other phases, so there's a maximum. And then there's an early cutoff. So if you find that the two vehicles, the successive vehicles, took more than 4 seconds, you assume nobody else is coming, and you early return to, so you send the green to the other one. So these are the three main parameters, right? The minimum green, a so-called extension, and a gap out or a max. Gap out means the two successive vehicles took more than 4 seconds, or whatever the gap out. So that's roughly the logic. Okay. So now we're looking at phase 4. So what is phase 4? Oops. So phase 4 is this green. That was the through traffic. Now there's a reason. What you'll notice is that green there's at least gives you minimum this much, right? And why is that? And that is because it's a fairly wide street, and this green, which is, so when this is green, pedestrians are allowed to cross. The pedestrians have to make it to the other end safely. So there's a minimum green, which is given for the pedestrians, right? Beyond the minimum green depends upon how much traffic there is. So that's the minimum green. Okay. So you can take the histogram of D4, and you see that it's minimum at least this much. That's for the pedestrians. And then it goes up, and it's got this shape. The shape, the histogram. So this shape comes from, notice an extra vehicle, and so the extra vehicles, so this probability time, so the green got extended, and so on. Okay? Now, we're somewhere t seconds into the phase P4, right? So it's still green, and you want to know how long it will continue. Well, there's an obvious thing you do, right? At any time t, if you're here, so 34 seconds have passed in that phase, and you are required to predict to the vehicle how long that phase will last. What will you do? You take the expected value of the remaining duration given at time t. That's right. If t equal to 30, you do what is the prediction of D4? It's still green, so D4 beyond 30, so that's your best prediction, or a prediction. Okay? You do the best if you do mean square or something like that. That's the conditional expectation of the remaining duration. So if you're here, this would be a bulk of your prediction. But if you pass that, you'll worry much later, right? So what will it look like? So let's go back to the prediction. The expected value would be around 38 if you're somewhere here. I've forgotten whatever the time is. But beyond that, now your prediction is increased if you have already passed 36. And so on, right? So if you work it out, that's what the prediction will be. So if you're the prediction provider, you need in your whatever, some lookup table, the time. And if already 38 seconds have gone by and you're still green, then you'll say it'll last up through 42, so the remaining duration is 42 minus 38, and so on, right? So that's your best prediction. Some interesting thing. If you look, so this is now the duration, remaining duration, D4 minus T. And what you observe is initially it'll decrease. Of course, time has gone by, so you expect the remaining duration to decrease. But then all of a sudden, your best prediction goes up because you passed that small thing, and now the next big probability is somewhere there, right? So, and then it goes back again. This is like your file downloads, right? And the time goes down, 5 seconds, 4 seconds, 2 seconds, then all of a sudden it goes up to 5 seconds, etc. Now, so the residual phase duration may increase or decrease. That's the nature of the actuated signal. Now, one reason people are proposing that they should have a SPAT intersection should provide you the SPAT signal is for so-called eco-driving. So eco-driving is I've arrived at the beginning of the intersection, and I want to go through the rest of the street. And most of the energy is consumed in acceleration and braking. If I know that this thing will be green in 20 seconds from now, then I can adjust my velocity profile so I don't do acceleration and braking and make it in the green window. So that requires me to tell you the SPAT prediction. But this kind of story, because the prediction fluctuates, makes it difficult to do eco-driving. So Audi has now announced they have something called a countdown timer, which gives you how long the green will last, or when the green will start, one way or the other. But it cannot be just a countdown timer, right? It also has to allow a count up in the thing. So I'm not sure exactly what they mean by that. Okay. So let's see how you do this eco-driving. Right. So how would you design the variable speed profile of this vehicle going through that link? So this is the naive user who's uninformed, doesn't know when the red is going to happen and when the green is going to happen, and has started the whole thing is 400 meters, and it started at 22 meters per second and just goes constant speed. It'll hit red and then have to stay until it hits green and go on. Right? So a lot of energy is going to be wasted in the braking. Okay? So that's the so-called naive user. Now, if you're doing an eco-driving, so you are going to design the speed profile of your vehicle as it goes through that intersection when it receives the SPAT signal. So that's in the subsequent stuff, this is the model for the fuel consumption, which depends upon the speed and the acceleration of that particular vehicle. And as you expect, it's increasing with speed and increases with acceleration. Right? If it's negative and they're decelerating, then you just pay something constant. Otherwise, that's what you get. So given that, we're going to design, and given when the light is going to turn green, we're going to decide.
Can you say what is A?
I'm sorry?
The A
is the acceleration. This is decelerating. This is accelerating.
But isn't that under your control as well? Is that it?
Oh yeah, it is under your control. So I haven't yet said, but this is the way your fuel is going to be consumed.
All right.
Okay, that's the model of the fuel consumption. So you're going to go from beginning to end. That's the model of your fuel consumption. So what's the V of t, or what is the A of t, and therefore the V of t, which is its integral, how is that going to be designed? Okay? So here's what the fuel consumption looks like as a function of speed. I mean, it really increases fast with speed, right? Typically, if you're driving at a constant speed, then the drag is what you have to combat with gas, and that's the way it goes. If it's the acceleration is 1 meters per second, and so on. Okay? So the problem is, if I tell you when the red will change to green, so that's the time t red, if I give you that ahead of time at time 0 is when you're entering this, leaving the previous intersection and entering this stretch of road. And I'll tell you what that is. This is the amount of fuel you'll consume from T0 to TF. TF is when you reach the end. So D meters is how long that road is. Okay? So the standard control problem, perfect information, so I tell you how much, 15 seconds, 20 seconds, 2 minutes, whatever. So you want to solve this, so discretize everything. So that's the discrete formulation. And you solve it by dynamic programming, go backwards. We know what the boundary condition is. You have to reach D. And here's what it looks like. If you start out at 25 meters per second, and you want to hit this when you're green, I mean, you don't have to, but if you hit it in red, that's bad, because now you're going to break a lot and waste too much energy, right? So obviously, you should hit it so you just enter exit the road when you're in green. So that's what these profiles will look like, okay? So if you're starting at time 0, you'll go this way, and then you realize, not you realize, you know it ahead of time, so your velocity profile should be like that. Okay, and then you clear the intersection. At the end here, it's becoming red here, so you're squeezed a little bit. You have to make it through during the green, so you have to speed up a little bit faster than if you're in here. So this all makes perfectly good sense.
Why would it make sense to change the slope as opposed to just choosing a lower slope at the beginning?
I'm sorry?
Why would you not choose just a lower slope at the beginning?
The lower slope over here.
Yeah, instead of changing the slope.
This is the optimum, right? So there's a trade-off between speed and acceleration. So there's a. Okay, I'll go back.
This is for an initial speed of.
I'm starting. That's my boundary condition. I entered this road at whatever 25 meters per second.
That's for the given initial speed.
That's given. So different initial speeds will have different profiles than this one, right?
So that was an example where the initial speed is too fast in some sense. You have to slow down.
In that respect, yes, yes. Okay. But let me tell you what is too fast and what's too slow. I mean, it's too fast because you see this, right? But otherwise, so this fuel consumption is milliliters per second. But that's not the best. What speed should I go? If my road is very, very long, right? So I'm not going to hit that red for a long time. Then the speed I should go is the speed which is the least milliliters per mile, not milliliters per second. So I have to take this and divide it by the speed and so on to get the optimum. So the optimum speed is somewhere between that slow thing and the fast thing, right? If it was a long way to go. Yeah.
This is assuming single vehicle or a fluid?
One vehicle. No. So the other vehicles presumably will just follow you right in this. All right. So I have very little time. So I'll just finish the story. And right. So we've done experiments, and the experiments say that you save up to 20% of the fuel cost. Okay. So here's an example of fuel consumption. So this is the uninformed user at 20 miles per hour. And this is the informed user at, initial speed 25. You save a lot, right, of thing. And as the speed becomes the ideal, you begin to save less and less. So time. This may be interesting. So this is the fuel minimizing trajectory, and that's the naive guy. So you do take longer, right? If you're minimizing your fuel, then the time that you take to reach there, right, is more than, so you are driving slower than for this particular example. Now suppose we have this interesting case where the prediction varies as time progresses. Right? And it may happen that the prediction is in the middle of your driving, the thing changes. So I won't bother you with that. So then depending upon the number of steps, these people who came here, so it was initially this red, this was the time, then it became this, and then it became this. These people, unfortunately, it's too late for them, so they will have to stay red. Right? These people are a little bit better off, and they slow down, but not sufficiently, and then so on, right? Until these make it into the green. So let me conclude with one more So there are other SPAD applications. One is in safety that I think I talked about, which is it'll inform the vehicles how long this phase will last and what the next phase will be, right? So you want to make a left turn. You can't do it now, but it'll tell you how long you need to wait to make a left turn, so whether you should risk it or not, right? So that provides you that. More importantly, it'll tell you what are the phases of the other users. Because right now you just see your green or your red, and you don't know whether the other ones can take a left in front of you or cannot take a left in front of you, so that would give you. Perhaps a more interesting thing is for trucks and buses. So streets get chewed up by heavy vehicles. Your light vehicle doesn't really affect, right? Because the chew up of the street depends upon the cube of the weight. Right? So a 5-ton truck will chew up lots and lots, much more of the roads. So in Berkeley, if you notice, I don't know in wherever you come from, in Berkeley, if you notice for buses, at a parking where the bus stop is there's an apron of concrete. So the bus comes and stops over there, right? Because the biggest wear and tear happens when it's braking and when it's accelerating, right? That's when the maximum torque on the wheels, and that's when the torque goes to the pavement, and that chews up the pavement. Trucks are even worse than buses. So if a truck is coming, it knows where it is, perhaps from the GPS. So it knows if it gets a signal saying this thing will last for 15 more seconds, it can adjust. Right? Or even better, maybe the intersection can give it more green so that it goes through without hitting the brakes. Right? Typically, buses are given that privilege. So buses have many intersections. The buses have a special signal, so the intersection gets saying the bus is arriving, and it may give it and extend the green for the bus to go through. Right? If the bus is going squat in the middle of the red, then it's not going to do that, but it'll do that. So this can help a lot in terms of infrastructure and pavement lifetime. So I'll stop over there. Yeah?
So won't it happen that in the morning people go to work and then in the evening they come back, so there are different traffic patterns, and so you have to adjust the timing?
So you should adjust the offsets, and you should adjust the durations exactly according to, you should take it into account. So typically, in terms of durations, a signal controller has space for 16 different patterns. And they'll hire a consultant to figure out when the morning commute time, whether it should start at 6 a.m. or 10 a.m., and then the midday and evening, and so on, right? It'll be much better. But that's, you have to know what the traffic volume is, right? So, but if you had those measurements, and now they're not difficult to get, then you should have those adjusted on the fly, as it were, right, in real time. And even though there's a commute pattern, still, it may be 15 minutes early or 15 minutes late, and if you know that, you can change those timing and get a big advantage in terms of throughput and reduction in delay. So you ought to do that. So if you go to your city, you should tell the traffic engineer to make it adaptive, right? Because, today, collecting that data is easy. It's not Google-style data, right? You need volumes. It's not just what is the travel time, but you need volumes, and you should do that. And it would be nice if you develop algorithms which can do that offset as the traffic pattern changes, right? Because that's a difficult problem. Yeah.
Is there any analysis of robustness with respect to, say, disruption? I'm thinking like Mountain Avenue and I-210 clogs.
There isn't, right? But that it certainly affects travel times, and so it should affect offsets, and maybe it should also affect the durations, because this thing is blocked, so there's no point giving it green, right? But there isn't.
So the main reason to have a fixed cycle time is just to make the offset problem easier?
Yes, otherwise there's no, offset doesn't make any sense, right?
Is it possible that that if you kind of have slightly flexible cycle time, then the offset problem also might become easier? Or I'm not sure.
I don't see that. I know the offset problem is ideally you want the offset to equal your travel time, right? So you get a green wave. And indeed, the travel time changes continuously, right? Now, I understand that. But you cannot change the offset continuously. I mean, this is centrally, has to broadcast, and it may be the travel time, this one has gone from 10 seconds to 12, but the next one hasn't. And the offset is, I mean, you have to adjust all the offset at the same time, as it were, right? Yeah.
So, sort of the perspective where you're coming from, the supporting infrastructure of all this, it's sort of some kind of a wireless communication and sensory data between the smart vehicles and the signal.
Oh, for this?
This is where you're coming from?
Well, I'm not sure entirely. I mean, no, but then I have to wait forever, right, for these smart vehicles to show up.
My point is that if I, live in a reasonably sized city in China these days, they will already have a countdown
Correct.
of all the traffic signals.
Absolutely.
How many seconds left in the green? How many
Absolutely.
seconds?
So I'm saying you should use that, but that is possible because they have fixed time, right? But in this, so I agree with you completely that you do not need connected vehicles. You can have timers. I mean, everybody uses the timers on the crosswalk, right, to give you some idea of how long that green or red is going to last. Well, make it explicit, then you can adjust it much better. So I have nothing. I'm not saying that you need to be connected. I'm also saying that you can also put on a little something what the next phase is going to look like. Who is going to get the right of way after the 5 seconds when your timer is over? No, so I'm not at all insisting that you need to be connected in order to take advantage of this, right?
Okay. So we'll break until 3:10.
I put one paper.